So, our sandbox model consists of three layers, namely the unconfined aquifer, aquitard, and the confined aquifer. For the unconfined aquifers, they are groundwater reservoirs that are not confined by impermeable layers. To create this in a sandbox model, the sand with low permeability due to finer specification is put in the uppermost part layer, allowing water to infiltrate slowly. This infiltration can be called an aquifer's recharge. Sand from Bantayan, which is the finest among all sand collected, was used. On the other hand, the middle layer, which consists of sand and gravel, enhances the aquifer storage capacity, where gravel can act as a reservoir that collects water before going to finer materials, which is the sand. Sand and gravel from San Remigio was used. For the aquitards, an aquitard is a geological formation which prevents groundwater flow because of its low permeability. Therefore, modeling clay was used to represent this layer. Then, a 0.2 mm needle was used to create small holes in a modeling clay, simulating an aquitard. Aquitards have low porosity, unlike clay, necessitating these artificial pore spaces. Lastly, the confined aquifer. Since the sand in the Compostela is much larger compared to the sand from San Remigio and Bantayan, the group decided that it would be best to use it as a confined aquifer material, which is found in the bottommost part layer of the sandbox model. Moreover, the depth of the four wells in the sandbox mimics different well depths in the real-world scenarios. So, to start with the simulation, water is manually inputted in the recharge area of the sandbox model to simulate precipitation. Observe that the water will flow downhill, simulating groundwater flow from areas of high hydraulic head to low hydraulic head.
Taking a closer look at the aquitard layer, it appears that it actually prevents water from flowing. Water will flow towards the confined layer only through the unconfined layer located on the right side. By the time that the sand in the model is saturated enough and the water table is higher than the well, water will flow into the well due to gravity. To simulate contamination in the model, red dye was injected into well 1. Assume that the contaminant refers to chemicals, bacteria, or other harmful substances caused by human activities, natural factors, improper well construction, and lack of well maintenance. Over time, contaminated water slowly spreads underground due to the natural processes of groundwater flow. The porous nature of the subsurface, combined with the forces of gravity and water pressure, allows contaminated water to migrate away from this injection point. To explain further the other factors causing this phenomenon, the first factor is hydraulic gradient. Water flows from areas of high hydraulic head to areas of low hydraulic head. Even if the water is initially injected into a well, the hydraulic gradient can cause it to spread in various directions. The second factor is dispersion. As the contaminated water moves through the soil, it mixes with the surrounding clean water. This process, called dispersion, causes the contaminant to spread out over a larger area. The third factor is diffusion. Contaminants can also spread through a process called diffusion, where molecules move from areas of high concentration to areas of low concentration. This can contribute to the spread of contamination, especially over longer distances. To determine if contamination from well 1 had spread to well 2, water samples were extracted from well 2 using a syringe. Comparing the original blue water as recharged to the reddish water extracted from the well, we can visualize the impact of contamination.